Questions about anything? Or I just want to tie up some loose ends today about the material in Chapter 7 about integration. So we'll be completing Chapter 7 today. One thing I didn't mention that's in the section on 7.2 is the change of variables formula that you learned in freshman calculus. So it was a tool for calculating integrals like the one I have here. And what you did in freshman calculus is you would wish you had a 2 here. And so you'd give yourself a 1/2 out front. And then when you look at this, you'd say, okay, let's let u be equal to x squared. And then the reason I put that 2 there is because that's du dx. This is du dx. And then we have dx. And so that would be equal to 1/2 the integral of sine of u. Du dx du, we write a shorthand for du for that, and write this is the integral of sine u du. And that'll be 1/2 times minus cosine u plus c. And so we get minus 1/2 cosine u is x squared plus c. Okay, that's what we showed you how to do in freshman calculus. Nowadays, now that we've done some careful proofs involving integrals, let me show you the change of variables formula is theorem. Integral from a to b of f of u of x du dx dx is the integral between u of a, this is the definite version of it, and u of b of f of u du. And so in freshman calculus, when we wanted to make you believe that fact, we said you just, well, actually I would actually prove it. It's just you doing the chain rule backwards. Okay. And that's sort of an accurate thing to say, and I would get away with it. But now that we know the careful proof of the fundamental theorem of calculus, I can let's say how do we see this as the chain rule backwards? So the proof is just going to be the fundamental theorem of calculus plus the chain rule. And so let's see, to make this look like the chain rule, I need to, we know that there's an antiderivative of f given by the indefinite integral. So let's let capital F of x be equal to the an antiderivative. So be such that f prime of x equals f of x. The fundamental theorem of calculus showed us a way to find one of those as the integral from something to x. Okay, and then this thing inside the integral would be the derivative of something. Let's see, we'd have the integral of ab f of u of x times du dx dx. That little f would be the derivative of something, so that would be f prime of u of x. And that's where we realize, oh, that's just the chain rule now. And so this thing inside the integral is the derivative of a composition. And so now the fundamental theorem of calculus would say, aha, that's f of u of x evaluated between a and b. And f, yeah. So that's f of u of b minus f of u of a. And of course, that's the integral of f of u du between u of a and u of b. Same thing. Check. So use the fundamental theorem of calculus 2 times there. Anyway, that's a careful demonstration of that fact. Questions about anything that? Let's see. I wanted to use the Darboux version of Riemann integral because it's so kind of clean and beautiful, and a lot of the demonstrations are less messy because it just is a clever, clean way of describing the thing. But Riemann got famous for the way he described the Riemann integral. So Riemann's version. Let's see, it's going to be very similar to the beginning part. We have an A, which is an x naught, and a B, which is going to be an xn, and we partition it into subintervals. They can be different lengths. Dot, dot, dot. And the last one would be xn. This would be xn minus 1. And that's a partition. We'll still call that a partition. And then, the Riemann integral that I drew in the first day involved either taking Riemann sums with left endpoints or right endpoints. But you could choose any point in that interval. So let's call this C1, a point I pick in there. This could be C2, a point I pick in, could be an endpoint, could be a left endpoint or a right endpoint, etc. C3. And then this last one would be an xn. I can make it be a left endpoint if I want. Okay, so when I give you those points, they're called tags. Then we denote that partition with tags by a p dot. Okay, and so the deal here is that Cn is just any old point in the interval from xn minus 1 to xn. Okay, P is a partition. P dot with all the points in it is called a tagged partition. And then there's another thing I'm going to call the mesh. It's going to be, we're going to call it like a norm of P, or I can put a P dot there if I want. That is going to be the maximum delta x. So that's the maximum as n goes from 1 to capital N of xn minus 1. So that's the biggest delta x. Okay, then the Riemann sum associated with all this junk would be called S of P dot function, and it would be the sum as n goes from 1 to capital N. We'd evaluate the function f at the tag points. Could be left endpoints, could be right endpoints, or any old point. And then we multiply by the length of the delta x, which would be xn minus xn minus 1. And that's an approximation to the area under the curve. Okay. And Riemann's definition of the Riemann integral is, so here's the definition. We need the function to be bounded for this to make sense, because you sure wouldn't want to stick an infinite something. You wouldn't want to let c go off to infinity and blow up. So let's see, definition. Let's suppose f is bounded on AB. We say f is Riemann integrable and we've been writing that f is in R of AB. So we write that and we say the book likes notation integral from A to B of f with no dx. That's kind of a snazzy math way to write it, but most books prefer to write it in the classic way, like that, freshman calculus. And we say that's equal to L if, here it is. So I can't write this as a standard limit because, standard limits have been defined in terms of epsilons, deltas, and very precise wording in terms of functions of x. But it's very similar to that. If, for any epsilon bigger than 0, no matter how small, there is a delta, which might depend on epsilon. I guess I'll add all these words. There is a delta, which it probably depends on epsilon. Such that the Riemann sum S for a partition, tag partition F minus L is less than epsilon whenever the mesh of that partition is less than delta. So whenever P prime is a tagged partition of AB with mesh less than delta. Okay? And it's a fact that this is exactly the same as the Darboux integral definition. So fact equivalent to Darboux's. definition in section 7.4 that I started with. And the demonstration of that is on the proof is on page 232. It's just a couple paragraphs. And I should say there's a Cauchy criterion for this version of the Riemann integral. It's very similar. If I have I'll let you read about the Cauchy criterion for this version. Okay. Here's a fun thing to think about. Last time I showed you that the trapezoid rule I showed that the actual integral of f of x dx minus the trapezoid rule sum. Let's see, what's the trapezoid rule sum? Sum as n goes from 1 to capital N. The trapezoid rule formula is, what is it? Darn. Should be hardwired. Oh, yeah, I remember what it is, but I'm not gonna write it down. Minus the trapezoid rule formula I used the mean value theorem and showed that this is less than or equal to m times b minus a cubed over n squared, where the m is the biggest maximum. It's the max of the second derivative of f, so I assumed it was C2 smooth on AB. And the delta x in the trapezoid rule is b minus a over n. This time I'm going to think about the rectangle method, which is basically the Riemann sum. So the n squared there is exciting because you can make, if you take a big number n squared is even bigger. And so you can zero in on the actual numerical value of the integral pretty efficiently with an n squared there. So the question is, how good is the rectangle method? The rectangle. It's not very good. It's not nearly as good. Okay, let's do the rectangle method with left endpoints. So, an example, let's do left endpoints. So the integral would be approximated by a sum as n goes from 1 to capital N. I take the left endpoint, which would be f of xn minus 1, times the delta x, where the delta x is equal to b minus a divided by capital N. Okay. And so we're going to take the actual integral minus that sum and analyze it. And so if you think about on one of the intervals, we'd have here xn minus 1, xn. Our function is doing something up here. And we're approximating by this rectangle. This is an f of x n minus 1. And so our approximation to this area under the curve is the area of this rectangle. And so if we look at the error here, it would be the integral from xn minus 1 to xn of f of x dx minus that rectangle. Times delta x. And you think about, how can I stuff those together in a way that I can analyze them? That area into that rectangle is the same thing as the integral from xn minus 1 to xn of the constant function f of xn minus 1 dx. And when I look at it like that, I realize that I can write it as, I can stuff it under one integral, xn minus 1 to xn of f of x minus f of xn minus 1 dx. And now I'm going to think about that thing inside the integral and think about how big it could be. So let's look at this thing here. That kind of looks like, let's see, where have I seen something like that? I've seen something like that. F of x minus f of xn minus 1 over x minus xn minus 1 equals f prime of a c, where c is between those two. That's the mean value theorem. And so that means I can write f of x minus f of xn minus 1 as f prime of c times x minus xn minus 1. That's kind of exciting because then I realize I can estimate how big that is. So, So the absolute value of f of x minus f xn minus 1, that would be f prime of c times x, well, x bigger than x minus n minus 1. This thing's less than or equal to delta x on that interval. And let's make this less than or equal to the max of the first derivative. So where m is the max of the absolute value of f prime on AB. And so when I estimate that integral, the integral from xn minus 1 to xn of f dx, let's see, the thing was minus f xn minus 1 delta x. When I use that's less than or equal to the integral from xn minus 1 to xn of the absolute value of that stuff. And I just estimated the stuff inside to be bounded by m times delta x. So this stuff I just estimated to be less than or equal to m times delta x. And so this whole thing is less than or equal to m times delta x. That's the biggest thing inside the integral can be. And remember, over here we put the length of the interval. That's also delta x. And so I get a delta x squared. That's called the local error. It's like the local error is delta x squared. And now when I add them all up, so I've got, let's see, what is this thing? This thing is m times b minus a over n squared. And I've got n of those. So we have to, when I add them up, if I go all the way from a to b of f of x dx minus the rectangle method formula would be a sum of n local errors this is the local error. And so when I multiply that by n, I would get that this is less than or equal to m times b minus a squared over just one n. So it's not nearly as good as the trapezoid rule. And if you experiment with it, it takes you forever to get honed in on the integral using the rectangle method. And it's so bad that usually the round-off error starts contributing in a key way to the error. So that's pretty stinko compared to the, so much worse than the trapezoid rule. So there's an example of how you use the mean value theorem to estimate those errors. The ultimate the super duper method which you might have learned in freshman calculus, we used to emphasize it more. It's called Simpson's rule. And there, you partition the interval into an even number of intervals. So the partition and you'd, let's see, you'd have these even number of things, and you look at these three, and you, instead of approximating by trapezoids or rectangles, you would approximate by the best parabola. You can fit a parabola between these 3 points. So let's see, it would be, that's pretty bad. I should make them closer together so you can. Let's see what I want to do here. This is going to be a curve, and then I'm going to have 3 points here. And it turns out that 3 points determine a parabola. So there's exactly one parabola that goes through those 3 points. So it's a parabola. And you can actually write down an equation for that parabola. And you see that it so well approximates the curve that the error there is that little tiny sliver, the difference between the area under the blue curve and the area under the orange parabola. Okay, so you need an even partition. So you can do those 3 points like that, and you approximate by the parabola, and you can find the exact area on the parabola and write a formula for it, and you get the Simpson's rule. And it turns out that Simpson's rule converges much faster, so I'll let you read about it in 7.5. What's the magic thing? The Simpson's rule error is, let's see, what is it? It's B minus A over 180. What's HN? I think HN is yeah, that's what I thought it was, sorry. HN is B minus A over N. Times, let's see, so the maximum of the fourth derivative on AB. And this is to the fourth power. So the trapezoid rule is a square. Simpson's rule is to the fourth power. And so it's incredibly much better and faster, because n to the fourth, it goes blasting off and getting big real fast. So in fact, you can get kind of extreme accuracy if you're with very few points in your partition, which is fantastic from the point of view of numerical analysis, because round-off error can be a major issue when you're trying to approximate things numerically, especially if your machine 0 is only 8 decimal places. Let's see. Yeah, so the book describes those things. I could have been much more careful in my trapezoid rule and got it, you see that 180 in the denominator there? I could have gotten a 12 in my denominator if I wanted to be super careful. And in fact, there's sort of a super mean value theorems can be used in these things. You can replace this, the max here, by a fourth derivative at C. So it's actually equal to that for some C in between A and B. This is kind of a fancy mean value theorem for analyzing these errors. Anyway, this is handled in section 7.5. It's a good thing to read, I think. I've described rectangle method, left endpoint, and the trapezoid rule. And I've been not as fancy about it as the book, which I think is the way you should see it the first time you see it. Let's see. Are there any questions about anything or requests about anything to review? Or any homework questions? I'm deciding what to do for the rest of the course. There's some important things that we need to talk about in Chapter 8. important subjects. I'm not going to do all of Chapter 8 before the end of the semester, but there's some important subjects in Chapter 8 that I want to make sure we touch on. There's an important concept of convergence, and that's a uniform convergence of functions. On an interval. Okay, and so it's about not just a number going to another number, but a whole function going to get close to another function. So we write fn of x converges to f of x uniformly on AB means, given an epsilon bigger than 0, there is an n, a positive integer, capital N, such that not just at one x, but at all x's in the interval, fn of x minus x, f of x is less than epsilon. And so here's the uniform is, you get this estimate for all x in AB when n is bigger than capital N. So the word uniform means one n works for all the x's in the whole interval. That's an important concept of convergence. And so the big facts, let's see, I should talk about pointwise converges. Pointwise convergence simply means that fnx tends to f of x for each x. So uniform convergence is a much stronger concept than just mere pointwise convergence. Well, the big fact everybody needs to learn in this class, because it's going to get, in future classes, people are going to say, you learned this in Math 341. And it's sort of at the end of the semester. And some people forgot that they learned it. So the big important fact uniform limits of continuous functions are continuous. I want to make sure we get to that, so I'm going to do that next week. I also want to make sure we have some fun with some classic analysis things like convergence of Fourier series. So that's my plan for the rest of the semester. Let me draw the picture of uniform. Let's see, here's an interesting thing. The picture of uniform convergence means, let's say we have an f of x that looks like this. Then we go, here's a dotted line of f of x plus epsilon. Oh, that's crummy. Let's see, what can I do? I'm going to cheat. I'm going to copy that. And now I'm going to turn that to orange. There's plus epsilon. And then I'm going to do it again. Turn it to orange. There's minus epsilon. And so the orange ones are f of x plus or minus epsilon. And to the uniform convergence means our functions fn eventually get stuck in here. So they'd be wiggling, they can wiggle around. Well, that one got too wild. They can wiggle around like crazy, but they stay within this band. That green thing would be fn of x. And they'd have to be stuck in that band on the whole interval from a to b. And if you ask yourself why pointwise convergence isn't good enough, I could show you a classic example why pointwise convergence can be disappointing. Oh, let's see, what the classic example is. I have a function which is mostly 0, and I'm going to make it have a, let's see, I'm going to make it get gigantic. This is going to be 1 over n here. It's going to be 0 from 1 over n out to 2, but how about? And then here I'm going to make it be something gigantic. Let's see. This will be 2 over n. And then I make a gigantic TP here. That's no good. Okay. Those f, this is a f sub n. Those f sub n's tend to 0 pointwise, even though they're gigantic on this whole thing. In fact, I could make them have an integral. If I make this big enough here, I could make this thing really as big as I want. I could make the area under that little TP as big as I want. And so what I have, this example is interesting because it's a bunch of functions. Fn of x converges pointwise. At each point, pick a point, it converges to the 0 function. But they get arbitrarily big. They're not even bounded. So they converge pointwise, but the Fn are not even bounded. And for example, I could make the area of that TP be 1. Make the area of the TP equal to 1. What?
The 2 over n should be on the right of the 1 over n.
Yeah, I should make it 1 over 2n. That's what I was thinking. 1 over 2n, the middle of the TP. I make big enough that I can make that area be 1 over 2n. I mean, make that area be 1. So the Fn, of course, they're getting bigger and bigger. They're not even uniformly bounded. And I can set it up so that those integrals don't go to 0. The integral from 0 to 2, they're going to 0 point-wise, do not tend to 0. So especially when you study Fourier series, when functions converge, you want the integrals to converge. And here's an example of functions that look like, oh, they tend to 0 at every point, and yet their integrals don't tend to 0. It's because they converge in a kind of a crummy way. To get control of that kind of thing, the concept of uniform convergence is needed. And the last thing we're going to do is demonstrate the famous Weierstrass M-test. Let's suppose, here's what it is. Suppose the Fn are continuous on a closed interval AB, and suppose that Fn of x is less than or equal to some number Mn. Then if those Mn's are small enough that their sum is finite, then the sum of the Fn of x's converge uniformly to a continuous function. That gets used a lot in future analysis, especially in Fourier series. Converge uniformly on AB to a continuous function. F of x. Let's see, a continuous function on AB. Okay, it's not going to take long and it's not going to be hard. It's just a matter of saying the right words and seeing how they fit together. Okay, that feels like enough for today. So the exam 2 is going to be released at 5 p.m. on Monday, so I can answer any questions you might have about anything in class on Monday. I'm going to hold class like usual next week. Okay.